Like Professor Vargas has said, I usually remember that the exterior product is absolutely independent of the metal. Okay? So it can be attached to any kind of any resistance. So because of this projective geometry, maybe this is explained with the exterior product of points. However, this will not be explained in the summer school for long. But the idea is that exterior product, that exterior product is absolutely independent of the metal. Only deals with linear dependence. Without linear dependence, vector space, and so on. Okay? I explained to my pupils, but you have not been my pupils. I explained to my pupils that we can make linear algebra in two ways in high school. Only linear algebra without any kind of product. So linear combinations and so on. And then we introduce exterior product and we remake the linear algebra and exterior product and alternatives. Okay? So linear algebra and exterior product are absolute bases, but they are independent. But this is not the question now. Thirdly, I wish to show you what you have in your state, in your PDF. Okay? Is in this folder. So let us see one moment its contents.
There's a mouse if you want to use a mouse.
Oh.
If you want to use a mouse, there is one.
Okay. We have here the professor's account, draft of a book he is writing. It's a draft of a book about dimensional surfaces. Go back. We have here materials about geometric algebra. We have the first is a lecture about basically for everyday calculus. Chapter Clifford is material of mass. Clifford gymnastics is also fossil, definition of Clifford. We have here, I believe, a very important material, which is the early proceedings of the Algebra Conference 2016 of the right last year. Here, not all, but there are some papers about Clifford algebra and other papers about other subjects, but the interesting thing are those about Clifford algebra. There is an index, so you can see which are the papers they use. This material is a summary of Professor McDonald in the United States about geometric algebra. One of the best surveys of geometric algebra that has been published very recently in applied Clifford algebra, in advances in applied Clifford algebra, which is a journal where you usually publish this kind of papers. Okay? It is free. It can be downloaded from the website of Professor Ramon. This is the paper Chemical quantum mechanics that it is posted at the website, our website. And this is some book which is not my favorite, but at least some text that you can use for projecting or for working with your pupils. Okay? There are the basic things, and I also thought about people coming from developing countries that cannot have money enough to buy my book. Okay. Then this is about the subject of geometric algebra. We have here logistics, some maps of Sophia, Sophia, travel info dynamics and mass. And this is folder with information, with some facts about software. We have now in this meeting two softwares. One Professor Ramon. I believe that it is the best at this moment algorithm algebra in the world. Let us remember that Professor Abramovich made his doctoral thesis with Dracula, who made also a software, but a software model in this DOS. So it's an old software, and the new software over Windows is that of and symbolic, because Professor Abramovich's software is symbolic, and Clifford from Dracula. Clifford is not symbolic. Okay? Clifford may be downloaded freely from the website, from the mirror of the website of Dracula, since Dracula died in Crete. Okay? But it is over the
Sorry, may I interrupt just for not 1 second, 10 seconds. There's also the Clifford, which is numerical, and I hope that on Thursday, Professor Abramovich will be able to talk about both Clifford and Clifford. So it's optional there. You can choose the symbolic.
Yes, symbolic and numerical.
In numerical.
Yes, but the Clifford is only numerical. You can play with 2A1 plus 3A2, but not with CA1 and okay? And the other new software, which is being now developed, is by Prof. Has developed a software called geometric algebra over Maxima. Maxima is a free software available on the internet. And Prof will give us a lecture for today on Friday, and we'll explain all this. Okay. And the other things, Maple files are the software of Abramovich. Maple is not clear in its license, and I hope that we will be able to work with Maple at the lab.
Yes. By the way, these files, they are for Maple 2017, which is the newest version, as far as I know, but they work with all the versions. It's not a problem if you have all the versions.
Okay. So, and I believe that the README file is an index that allows you to access to all the data files, not some of the files, but all the PDFs are available. Okay? You could here, for instance, in the proceedings. Basically, the notes of the Taylor calculus, the stereo calculus, and also the notes of the Taylor calculus about quantum mechanics, they are included in the early proceedings. Papers. Okay? So you can see this. That's all. And then let us begin with applications to brain gene. This is a paper of last year, but we will try to be live. So we'll have no we have the index here. The notes of the calculus, and here the applications to brain gene. 15. Well, the definition of the Euclidean plane geometry is very easy. Usually two vectors, the square equals to 1, which are incompute because they are orthogonal faces. Okay? So this is a Clifford product, and it is the same that an stereo product because they are orthogonal. Only half products differ if the two vectors are orthogonal, but this is an orthogonal process. So, a vector, one vector, there is one, is a linear combination of we can multiply vectors to have, if we make multiplication with components, we have this as is a star and this as is by vector. Okay? Just this is a complex number. Why? Because the bivector unit has square equal to minus 1. Okay? So that the multiplication of two vectors is equal to a complex number. The geometric algebra is the algebra generated but by vector space, vector geometric space, by multiplication of the elements of the matrix. Then the multiplication gives us, Jose has explained, elements of higher degree, or of higher degree, okay? Up to the last element, which is the pseudostar, which is the multiplication of all the bases. So the dimension of the Clifford function in general is the addition of the combinatorial numbers up to n over n, which is equal to 2 power. Okay? This is the dimension of the Clifford function. In 2 dimensions, we have 2 power 2 4 dimensions. It means 2 dimensions for vectors and 2 dimensions for complex numbers. But they can be multiplied between them. In your faculties, you have not seen the multiplication of complex numbers by vectors. This is new, this is geometric algebra. Okay? Anyway, the role of the complex numbers here, the geometry, must be clarified and well defined. The sense of what means a complex number, or what operation, what geometric operation is represented by a complex number. Okay? The researcher, the scholar who explained this before, was just Giuseppe Piano. Giuseppe Piano was interested in the fundamentals of algebra, as you know, but also in the fundamentals of geometry, as nobody knows. Okay? So when I searched for the papers of Giuseppe Piano, I found the Oberstende, which is 3 volumes, with closed sheets. Not open sheets, but closed sheets. It is not a cabinet. Okay? And then I need a knife to open the page of geometric algebra. The page of mathematics, well, already open, but the page of geometric algebra, not in Madrid, in the Complutense, and not in Barcelona, 2 times. So I thought nobody shall read this mistake, because I have been the first to open the page of the Well, then it brings us that the multiplication on the right of a vector by unitary complex number describes a rotation. Okay, rotation. Then we multiply the vector by a complex number, unitary complex number, the exponential of E. E is identified in geometric algebra as the bivector. Okay? So we have this. But this expression is only applicable to vectors, not to all the elements of the geometric algebra. Okay? If we want to write a rotation operator to all the elements of the geometric algebra, we need to split exponential into parts. It is okay. This is a general expression that may apply to any element of the geometric algebra, not only for French equation that always for every dimension. We have here the half-angle complex number and the polynomial of this half-angle complex number. In fact, we have here a complex number and its inverse, because this is the inverse of this complex number. So we do not need to have a unitary problem with this expression. This expression gives rotations, but for many calculations in plane on the page of algebra, it is easy to use this expression. One of the problems of the geometric algebra is the geometric problem, because the geometric algebra is an associative algebra. Okay? The stereo algebra and the geometric algebras are associated. But it is a property which is a numeric property that you can reduce two vectors separated by one place, and the result is the same. In more dimensions, this property is not fulfilled, but it is scaled by the following property. This is. In what dimensions, many dimensions, the relative property gives the stereo product of the vectors. It is not zero, but two times the stereo product of the vectors. Okay? This is, I believe that from the algebraic point of view, this is a very necessary property for working with geometric equations, solving problems, or solving. Well, this property with one vector and a complex number means the real order of that two vectors that means the conjugation of the numbers. This is the axial symmetry always can be written in this way, but now B is the direction vector of the axial symmetry. You have an axial symmetry, have a direction vector of any norm, because we have here the inter, so the norm is not important, and the interpretation for a relation of any. This is a general expression. You can apply it also to complex numbers, and the axial symmetry applied to complex numbers means its conjugation, because the order of the vectors is changed. It is not the same to do this multiplication that this other multiplication. Notice that the other has changed the sign. Okay? Has changed the sign. In fact, the multiplication of the vectors is equal to the multiplication of the norms multiplied by the cosine of the angle plus I and the sine. Geometric multiplication of vectors. This geometric multiplication, as was explained, can be split into scalar product and vector product, and stereo product. Sorry. The stereo product represents the area of the parallelogram formed by the two vectors, only the area. And the scalar product is related with the projection of this vector over the area. Okay? These are the general concepts that are available to more dimensions. So, with this short package, we can apply to many problems. These are some of these problems. We can apply to Fermat's theorem and so on. I don't want to enlighten the lecture. But the important thing is that geometric algebra always gives a quantitative result, not only a quantitative proof, as we can find in the books of geometry. Okay? You can find the proof of the Fermat's theory, but only quantitative, not quantitative. We have results for everything. Fermat theory, another theorem which are listed here. For instance, the Morley theory. The Morley theory, from an algebraic point of view, has been very hard to prove, but we have found also a result. This is the theory, and this is the Morley theory. Okay? If we draw these sectors or angles, then the intersections form an example line. Okay, there are quantitative proofs, but which is the direction of this side, or of this side, or of this side? Which direction? The directions are given only by geometry. This is at the end of some page of this paper, but we have this reference. If I can show you page. What's the page? Is this?
It's the you mean?
No, yes. No.
Page down, it's on top of the keyboard.
On top of the keyboard.
It's written in Swedish or something. It's not.
Yes. Okay, this is it. Here we have the side of the triangle is given by the algebraic expression. You have A, the values of the circle, the sign of the diamonds, and the direction of one side, BC, multiplied by the exponential of this combination. This is a quantitative. We can program this in a computer to calculate the direction of this is not possible with other with vector analysis and other kind of vectorial method. This is the novelty of geometry. We can compute everything. Okay? So we can apply this to other theorems. Morley theory, all can be found quantitatively. For instance, we have here the Euler's theory. We know the quantitative proofs that the center, the center, and the circumcenter are valid. Have the conclusion in the neutral theory. But which is the direction of the Euler's line? How can we compute the direction of this line? If I know B, C, A, the coordinates, can I compute the direction of the line? Only in geometric algebra. And the result is here also. OR is an vector. From the circumcenter to the center. A, B, B, C, C, A are the vectors of the sides. And A, B, B, C, this is a geometric product. This is not a scalar product. This is not even an exterior product. This is a geometric product. Another multiplication of three vectors, a geometric multiplication, and the result of this is a vector. In general, this vector is multiplied by the area of the private, which is an imaginary number, because it's a vector, and this multiplication is geometric, because it's a vector by an imaginary number. Okay? This is only geometric multiplication. It's not the classical problems of geometry prepared for a scalar product that we studied. Okay? This is geometric. You will not find this without geometric algebra. This is the power of geometry. everything can be complicated. Okay? You have studied probability and statistics. Now we have the sample space, and then we have the Boole algebra of the sample space. By construction of union intersection of the events, we can do all the Boole algebra of the probability. In geometry, it's just the same. We have the vector geometric space, the generating geometric space, and by additional multiplication of these elements in the geometric problem, we will all the geometric algebra, the whole geometric algebra. There is a similarity. Already explained by Dracula in his paper. Well, here there are other examples. And then we can go to the three-dimensional space. We rise the dimension and the number of elements of the algebra. Then, if the space is Euclidean, on the geometric, as for one and the other, we are the vectors of the vectors, the orthogonal. The multiplication of two vectors gives a scalar, it is a scalar number, plus a bivector. You see the basis vectors. Okay? This is a quaternion. Okay? Just this is a quaternion is called a Dracula. The ingenuity of the 19th century was to think that the algebra of the space, or the three-dimensional space, clear three-dimensional space, was quaternions. And this is not. Quaternions are only a short algebra. The whole algebra is the Clifford algebra of the dimensional. Please, this is the whole algebra. Quaternions are implied. They are a short algebra of the Clifford algebra. If you multiply quaternions between them, you will always find another quaternion. But the algebra is wide, more dimensions than really, it was curious because in the source book on mathematics, you know the source book, which is a recopilation of fragments of some of those who initiated some branches of mathematics. In the source book, there do not appear just how Hamilton defines quaternions. Hamilton defines quaternions as a quotient of vectors. As a quotient. As a ratio of two vectors. Hamilton says, we take a desk, we have two vectors, and then he defines the quotient of these vectors in this way. He implements with the and he says, well, I put these vectors, I can obtain them, but the quotient is the same. The quotient needs a ratio of lengths, needs this angle, two quantities, and needs the orientation of the desk, the quantities, and the angles, plus the ratio of to the norms. Four quantities. Therefore, this quotient is a quaternion, four quantities. Okay? Really, the difference between quotient and product is just the same if the norm is unit. If the norm is unit, you only get to multiply by the norm, the square of the norm. Okay? But this important chapter of quaternions, of the elements of quaternions, is omitted in the source book of mathematics. Because people do not want that this appears in the source. What appears? What appears later parts, further part about cushion of ISO of K, and so on. Well, with this we can deal with the three-dimensional space. We can find things as the Euler line of the centroid, the circumcenter, and the notch point, which is not drawn because it's difficult to draw, but the notch point is the point where the intersections of the lines given by the two points intersect with them. Well, the 3 points are collinear, and again we want to know which is the direction of this Euler line. This is only answered by geometry. And usually, as always the case, with geometric products, not with scalar products, even with stereo products, only with geometric products. The result is this. The vector volume from the circumcenter from each point, which is the direction of the Euler lines, is this combination, this geometric products of the sides of the of the edge of the tetrahedron. Okay? This result is a pattern, Then we must make the geometric product with this, which is a pseudoscalar, which is the volume of the tetrahedron, but it is a pseudoscalar. Then we have here grade 2 and grade 3, and the result is grade 1.
So each capital letter
is a point.
What means?
Each capital letter is a point. ABC and
letter is a point.
Yes.
Capital letters is a vector.
A vector, John, without separation. If there is separation, then this is a geometric.
Yes.
But this is a
affine space. We have points and vectors.
Yeah, more than affine space, Euclidean space. Because we have defined the basis vector as a sub I square equal to plus 1. This means that we are in the Euclidean space.
Metric is always increasing, never decreasing.
In the definition of the vector.
It's inside of the...
Inside the vector. Because
it cannot be variable. If you change metric, Clifford product is changing, Clifford algebra is changing, everything is changing. But this idea of variable metric you never consider.
No. From my point of view, with this changing is the basis. That you change from an orthogonal basis to another basis which is not orthogonal. Okay? But not really the Clifford algebra and the geometric structure, because always you can find orthogonal vectors. You cannot pass from one signature to another signature, which is the law of inertia quadratic form. But given a signature, you can always find an orthogonal basis. With this orthogonal basis, you can work with geometry. Also, you can work if you wish to make your life more difficult. You can work with a non-orthogonal basis, but usually it's not recommended, unless for students. Okay? But with an orthogonal basis, we can make everything. But always with a fixed signature. Okay? The signature is plus, which means Pythagorean theorem. Okay? If we take the metric tensor and we do normalization of the metric tensor, this will give us plus. Okay? Numbers, different numbers. And then by renorming them, changing the norm of these vectors, we find that we have one in the other side. But this is the usual process of orthonormalization. Okay? With the But you cannot pass from plus plus minus to plus plus plus. This is not possible. Okay? So we assume from our different vectors and we work. Well, many things can be done with Clifford algebra, but the idea is always we can find quantitative results. This is very important. And this has been forgotten in geometry because synthetic geometry is the geometry of qualitative facts, but not of quantitative facts. People usually criticize me because I want quantitative facts, not only qualitative. So, Clifford algebra is the suitable algebra for this. In this algebra, we can write notations with quaternions. This is now. However, notations with quaternions are usually applied to quaternions. Why? Because a quaternion represents a plane. So when we make rotations, the plane also rotates. Okay? So the usual way to work, for instance, in aircraft navigation is only with quaternions. But really, rotations can be applied to every element of the geometric algebra, also to vectors. Okay? In this way. This is a quaternion, and this can be a vector, can be a quaternion, can be an heterogeneous element of the algebra because this is fully general. This is fully general. In fact, this expression has led me to go inside the algebra, to mathematical representations, to relate this expression with similar transformations on matrices and so on. But in this context, these are the expressions for quaternions, for axial symmetries, you can change a quaternion for the dimension vector of the axis. Okay? And so all the transformations can be written in this way. We can
okay, I can give examples from the book. With space algebra, maybe?
Yes, this is from space algebra. This is from the Euclidean. Perhaps to say that reflections in the three-dimensional Euclidean space cannot be written in this way. Okay? But this is a problem, as I shall later, not a later also is a problem of incompleteness of the geometric algebra of odd dimension. Because the geometric algebra of even dimensions, all the isometries will be written in this way. Okay? All the isometries. But in even dimension. In the case of three-dimensional space, this is not possible. But if we extend to the geometric algebra of space-time, which is an even geometric algebra, then we are able to write all the isometries as a similar transformation of matrices if you wish to understand it. Okay? So the next step is the space-time geometric algebra. Yes, we must explain
okay.
The space-time geometric algebra.
Okay, initially we have a lecture together. My aim is to show something on the board about what you were talking about. About the space algebra, because I think it's very for space time. Okay?
Okay.
But can you please switch on the lights?
So